Good evening. Thank you for the kind introduction and for the honor of the invitation to be here as part of the Climate Congress. It's really been amazing to see the incredible work that's taking shape here at the Biennial. So this evening, I'm going to talk about something that all of you have imbibed today and most likely also washed your hands with, which is groundwater. But before I talk about the exhibition that John mentioned and the ongoing work that I've been doing on groundwater, and why in particular I spent about 2 years trying to make that globe there that's cut in half to model all of the aquifers of the Earth, and why I came to make models that actually are core samples of the Earth that hang as opposed to stand from the ground up like we usually think of a core sample. And why those models are hanging from the ceiling with mirrors underneath them, I'd like to begin with 2 measurements to contextualize my talk tonight. The first is 80 centimeters, and the second is 959 cubic kilometers. So 80 centimeters is how much the Earth has shifted its tilt between 1993 and 2010 because of the amount of groundwater that we've extracted from it. 959 cubic kilometers is how much groundwater was extracted from the Earth in 2017. That's effectively 2 Lake Eries. And as John had mentioned, I see this very much as the hidden front line of climate change. When we look at the 4 largest extractors of groundwater in the world, Pakistan comes in at number 4, and just the top 4 countries extract over half of the global groundwater extraction. Bangladesh is 6th, so the Indo-Gangetic Plains is one of the largest consumers of groundwater in the world. Now, the fulcrum, as it were, that has produced the annual shift of over 4 centimeters and 2 Lake Eries per year extracted are millions of these things that you are all probably all too familiar with, hand pumps and tube wells. Now, these are fantastic technologies because they transform groundwater into infrastructure. And tube wells and hand pumps are commonly used in places where municipal water supply is non-existent, unreliable, or often polluted. These are minor technologies with a global reach, and they tap into one of the largest distributed masses of fresh water on the planet, which is to say aquifers. And as you can see here, they do so in a variety of ways, with different depths and volumes of abstraction and extraction. Tube wells are typically constructed from perforated steel or plastic, sometimes even from bamboo pipe that is bored between 1.5 and 300 meters below the ground to extract water from an aquifer. They're typically driven by electric or oil-powered engine, and once the water is extracted, it might be consumed at the source by people or animals, or used, say, in agriculture, like you see here, of a tube well in situ, particularly in this case in Punjab for wheat. And though both of these that you see here are diesel powered, which is more common definitely in India, I would say, than in Pakistan, they're rarely used in the open like this. Oftentimes in a structure like this, which is an electric-powered tube well, or even like this one in Shalimar Bagh that many of us saw yesterday. And one sees hand pumps like this outside cities for drinking and washing in so much of the world today, or like this cast iron pump outfitted unironically with a plastic water bottle, or in an urban environment like here in Kanpur, where it serves people and water buffalo, or even distributed like here by water tank for sale, as it is increasingly being done in various parts of the world. Today, nearly half the global population imbibes groundwater on a daily basis, and over half of all of our agriculture is irrigated with it. These devices, as I'm going to share with you, have allowed billions of people to thrive, but they threaten to bleed the earth dry. Suffice it to say, my argument is the following: groundwater technologies are as significant to farms and cities as the elevator was to the early 20th century American metropolis. And while this has largely been reported, certainly in the United States, as a catastrophe in the making by the media, here are just a few screenshots of the New York Times about, say, the East Coast sinking, America using up its groundwater like no tomorrow, groundwater being used for more chicken wings and pizza, which was rather surprising to me. The uncharted waters and those that are thwarting its conservation efforts, all the way to policies put in place to balance urban growth and the availability of water in the face of scarcity and uncertainty. And certainly to looking at where groundwater levels are dropping and falling, especially in various parts of the world. However, little of this has looked at this in terms of how it spatially manifests. And so I've been largely understanding hand pumps and tube wells, and along with their owners and users, as reshaping space. And I've certainly weighed in on this in my own way a few years back when I penned an op-ed on the need to consider space and time as factors for replenishing aquifers for urban growth and agricultural production, again with a focus on shaping space. And my work certainly builds on an extensive body of scholarship and field work, like the pioneering work of economist Biri Dhawan in the 1970s, through climate and policy expert Navroz Dubash, who has researched how tube wells reshape social institutions, particularly in Gujarat, to rural economists like Tushar Shah, Taming the Anarchy, to even more recent work that's looking at technology transfer between the Sonoran Desert and the Arabian Peninsula in Natalie Koch's work. And I've been at it for some time, writing a kind of abridged biography of tube wells and water extraction from aquifers for this edited volume. And I suppose I came to it out of a sense of concern that, or feeling sad for tube wells. People have literally penned poems for canals, for rivers, of course, but nobody really writes anything for the tube well. It's a rather lonely technology in that way. So I'm not going to say that I wrote a poem for the tube well. I'm not going to try that tonight. But the work that I do looks at the ways in which this has shaped so much of the way that we live today in cities and farms. And certainly more recently at some of the work that I've done looking at its scales from, the scale of a model village that I'll talk about tonight to larger impacts of tube wells. Not so much as a kind of linear technological succession of, say, first we had canals, then we had tube wells. It's more a question of how these technologies get layered on one another. And I'm less interested in what technologies do, but more in how people oftentimes misuse them in unanticipated ways. So making use of groundwater is obviously nothing new. We have qanats that date back to 1000 BCE of tapping into groundwater like you see here, or they're oftentimes known as falages. Certainly we have things like the Persian wheel, which we believe came to the subcontinent sometime around 200 BCE for extracting groundwater by bullock. Certainly things like the mot as well, a kind of long-standing technique. And certainly we have constructed ponds or talabs like you see here that still dot so much of the landscape that are actually not only just rain-fed, but also tap into the, what we'd call in ecology, the hyporeic zone where groundwater and surface water meet. However, the portability of tube wells coupled with industrialization in the 19th and 20th centuries, along with the murky codification of groundwater rights in the Americas and Asia, made them well suited for military campaigns and for areas with little to no surface water bodies. Now, because of my interest in understanding this condition spatially over time, I've been drawing the different kinds of configurations of pump technologies across the globe and placing them in relationship to agriculture and urban growth. These drawings examine tube wells and hand pumps as lenses for observing a largely invisible yet critical infrastructure. And this critical infrastructure, I would say, is that portion of the Earth's invisible hydrological cycle that we know as groundwater, that again undergirds so much of our cities today and agriculture. Now, in 2002, the gravity recovery and climate experiment known as GRACE was launched by the US NASA and by the German aerospace industry to monitor differential in the Earth's gravitational pull to then model groundwater. So this satellite system, which was launched in 2002, was decommissioned in 2017 because one of the batteries died in the satellite. Is today still what is mostly used as the basis for so much of climate modeling today in terms of understanding the relationship between groundwater, rainfall patterns, urban growth, et cetera, in terms of modeling these conditions that I'm going to talk more about tonight. But what I'd like to do instead is imagine that if we took the Earth and we emptied it of all of its surface water bodies, so its oceans, its seas, so we would see both its topography and its bathymetry, so that which is, say, beneath in the ocean floor, much like Thomas Burnet did here in 1694. But instead of doing this to try and make the argument for the veracity of Noah's flood, we can actually take the gray satellite system imagery and map it onto the interior of the globe so that we can see groundwater potential in relationship to the surfaces of the Earth, and have a view into, at least on a macro scale, how the subsurface is being used to reshape and terraform the surface. So in this drawing, I cut a section passes through two of the principal sites of experimentation with groundwater, the Indo-Gangetic Plains and the Sonoran Desert. And here you can see the mapping of groundwater, exaggerated, of course, in the interior. And here the section kind of unfurled down below, and I'm sorry you can't probably see it so well. And here a kind of transect of taking that section of the Earth and laying it flat at the bottom. So again, trying to use drawing as a way to hallucinate on what these things look like that are oftentimes invisible or on the subsurface, and understanding those part-to-whole relationships spatially. And here then that globe that I was mentioning to you before that took a very long time to model, to be able to see the aquifers, to model the aquifers of the Earth in its interior. And some kind of close-ups of it here. So tonight I'll focus on two places that have really contributed mightily to those 80 centimeters and 959 cubic kilometers, the Indo-Gangetic Plains, Sonoran Desert. And I've been doing work in both these areas for the past almost 2 decades. Started, well, I guess in 2004, so it is now 2 decades. But before I talk to you a little bit about that, I think it's important to say that filling in the backstory to this work involves work that I've been doing to try and see like one of these beautiful mud-loving creatures known as mud skippers. And I've been trying to see like a mud skipper because mud skippers, like us, they can see clearly above water, but unlike us, when we go underwater, because of the way that water refracts light differently, that's why we see wavy. Well, they've evolved so that they can also see clear, like a fish. So these are incredibly mud-loving animals that can move seamlessly between wet and dry, hard, and soft conditions, and I think are useful as examples of how we might move past barren dichotomies that oftentimes define these binaries of, say, wet and dry, hard and soft, urban and rural. And I spent the better part of that decade, as John had mentioned earlier, seeing like a mud skipper to write my first book, Ganges Water Machine, which I'm not going to possibly try to shoehorn into this talk. But to suffice it to say that the principal argument of the book is that when we look at, say, the footprint here of the Ganga Basin, so you see Tropic of Cancer was Bay of Bengal. If we look at the rain-fed agriculture that you see here, and we're drifting obviously into the Indus right over here. So we're just right over there. And then we look at the irrigated agriculture, and of course we have the Indus over to your left. This is the most hyper-engineered landscape on the planet when it comes to both surface water and groundwater. It's a kind of hydrological machine or a hydrological supersurface. And when I say machine, it's less a device like the chronometer pictured here, which was used to assist with establishing longitude in the 18th century, but instead is more like Luke Skywalker's bionic arm in The Empire Strikes Back. Is it a technology with a biology, or is it a biology with a technology? So tonight I'll share with you some mud-loving moments that epitomize the virtues of seeing like a mud skipper and what they might augur for the way in which we expand our extraction of groundwater. So seeing like a mud skipper means attending to this substance silt. Ever since the subcontinent collided with Asia some 50 million years ago, trillions upon trillions of tons of silt have been shed from the ever-growing Himalayas during that tempestuous fire-water cocktail that we call the monsoons. And this silt is what, of course, makes the Indo-Gangetic Plains such a rich place for agriculture, and its choreography rewards scrutiny. Indeed, between 1 and 1.6 billion tons of silt are shed annually across the Indo-Gangetic plains. That's about 3 times the Mississippi. So it's quite expansive, the amount of silt that's being moved across this landscape every year. And I'd like to take you to a city in the center of the basin that I've been drawing for the past now 20 years, Allahabad, or what has been recently renamed in India, Prayagraj. Now, located at the confluence of the Ganga and Jamuna rivers, and for some a third river known as the Saraswati, this is one of the most sacred sites within Hinduism. As one can see here, pilgrims are alighted on board where the blue azure waters of the Ganga meet the brown-gray water, the blue azure waters of the Jamuna River meet the brown-gray waters of the Ganga River. And while at first blush, this might look like 2 bodies of water meeting, I tell you it's not. It's actually 2 geological provinces, because the sediment in the Ganga is very different than that of the Jamuna. So it's the kind of silt that's within the tectonic crumbs shed from the Himalayas and the Chambal River from the Vindhya Hills that are coming together here. So this is really 2 geological provinces and not necessarily 2 bodies of water coming together. And the drawing that I'm sharing with you here is a drawing that I did all by hand and by foot and by boat that combines cartography and photography to measure the rhythmic and cyclical conditions of the Ganga Basin, and in particular at Allahabad over a single year. So what do I mean by that? Well, this drawing shows how surface water bodies expand and contract over the course of a single year. So the lightest tones of violet are when we're just after the monsoon season, and the darkest tones of violet are when we're pre-monsoon. So you can see the ways in which the characteristics of especially the Ganga transform dramatically, especially because of the amount of sediment that's within the channel itself and the larger watershed. So throughout 2005 and 2006, I lived in Allahabad and would visit the Sangam every other week for the full year, where I would go and photograph the conditions taking shape there. So this is photographed during January, February for Magh Mela, which is an annual festival where 4 to 5 million people come to a tent city to bathe for about 30 days. There's running water, electricity. And this city is obviously temporary. When the festival is over, the outline of the grid of the city remains tattooed on the shoals and sandbars of the river. Farmers move in and use that former grid of the city for agriculture. So it goes from hyper-urban and dense to agrarian in less than 2 weeks. Farmers harvest their crops. The monsoons arrive, eroding the sandbars and shores, and completely washes away the ground. This process of urban to agrarian repeats every year. And this combination of photography and cartography captures these slow motion changes and the ways in which people build on the deep rhythms of the monsoons. And the drawing has been published elsewhere, mostly to depict a way to draw layers of a city ranging from its temporality and biophysical layers to social and sacred transformations as well. And of course, this is also the site of the Kumbh Mela, or full pitcher, which typically takes place every 12 to 13 years and is typically spoken about as being the largest gathering of humanity on the planet, because 80 to 100 million people come here over the course of 45 days to bathe at the river. And which is an incredibly large tent city full of hospitals, fairgrounds, pontoon bridges, pundals, and so much more. It's inhabited 24 hours a day. But what is more spectacular to me, that this tent city for millions of people goes from this to this agrarian space in just 2 weeks. All of the silt and sediment that's been collected here over those 50 million years acts like a sponge so that we don't even have to go more than 20 centimeters to hit groundwater, to irrigate crops like you see here. And as you can see here, the footprints of the tents and the avenues remain tattooed on the sandbars. It's a drawing at the scale of the territory. This is the most intelligent use of space that I've ever witnessed. It's a drawing. These processes provide, I think, a blueprint for how to build on these deep rhythms of the monsoon, a process that as more and more parts of the world experience environmental uncertainty would do well to better understand and learn from. Now, I began all of this work, as I mentioned to you, in 2004, and I think it's helpful to kind of situate what I was working with when I first started this work. The best books that I could really find were, say, Raghuveer Singh's The Ganges, or Avalanche of Statistics, Histories of Cartography, Eric Newby's Slowly Down the Ganges, where by the end of it, his wife divorces him because it was such an arduous trek. I think more going with him than going down the Ganga. But when I started this work, Google Earth had just gone live in 2004. Drones existed, but were mostly being used by the Bush administration to surveil and assassinate people. GRACE was active, but its resolution was about 300 to 400 kilometers per pixel. To give you some sense of that scale, most satellite imagery we get today is about 30 meters to the pixel. So it's incredibly low resolution. So all I had at my disposal was a clunky Garmin eTrex GPS unit and an even clunkier Nikon camera to do the work of examining this watershed. When I arrived in India in 2005, I'd hoped to find contemporary maps. The best I could find were oftentimes maps like this, which were really retracings of maps that had been drawn during the Raj and sometimes even before. So effectively, the basin hadn't been mapped by the Survey of India in over half a century. What was more, when I would ask to see maps, oftentimes I'd be asked if I worked for the CIA. I don't know anybody that does, and I can't imagine someone saying that they do, but so I never found any comprehensive maps of the basin. So I had to go out and walk the land. And I'm showing you these not because of how bad I look with long hair or a Texas Longhorns hat. I'm not from Texas. But because I had to become my own barefoot architect, historian, and cartographer. And so here I'm standing in a brewing dust storm of silt and sediment, which is being whipped up in March. And I think it's important because I came to understand the basin and the larger watershed in terms of its being water, mud, dirt, dust, deity, atmosphere, and so much more. So I went all the way from Gangotri Glacier, about 3,800 meters above sea level, through the Indo-Gangetic Plains, snapping over 25,000 photographs to create a near panorama of the basin, which is why this work took over a decade as opposed to a year to complete. And so Seeing Like a Mud Skipper led me to making my own prosthetics and instruments, as John had mentioned to you before, to visualize the dynamism of the basin. So because it hadn't been mapped in over half a century, I'd had to develop my guerrilla tactics for mapping this area. So this is the surface accumulation sleeve, which is a device that you wear over your right hand. You can see that clunky Garmin eTrex there. Space for my old school Nokia mobile phone. And then I had packaging tape attached to my arm. And much the way that Spider-Man shoots his web from his wrist, I would shoot packaging tape from my wrist for 1 kilometer perpendicular to the river, like you can see here, so that I could pick up soils, because the particle sizes of soils can tell you a lot about the behavior of a river. And I'm happy to talk more about that later. And here you can see the instrument as it was exhibited in Seoul in 2019. And here a kind of diorama where I used Walking Dead figurines to do these kinds of dioramas. And here a close-up of one of the iterations of the device. I used bobby pins to hold the Garmin eTrex in place. And here one that was a lot more comfortable, especially in 45 degrees Celsius conditions in doing this work. And here with a hoe to help pat down the soil. Because this work is quite uncomfortable, would hurt my back a lot, I repurposed a child's remote control car with these devices so that I could make my own rover, as you can see here, tricked out with packaging tape, torch, camera, and much more. And here it's kind of in profile, kind of above, which made it much easier to do this work. Now, because these rolls of tape get really big and accumulate a lot of stuff, as you might imagine, I devised what I call a Gunga dip sock, where I bought 100 pairs of white cotton tube socks, and I thrust them into the river channel to collect soils, and then dry them out and geotag them as a way to also do this kind of guerrilla tactics of mapping the river, so that when I went through customs, and if I ever got asked, well, why do you have so many soiled socks? I'd just say I was a filthy backpacker that didn't have time to do my laundry. And you saw my hair, so I don't think that would be too far out of sorts. But if I take you back to the tape just for a moment, along with being like Spider-Man's web, a colleague of mine at University of Tokyo, Catherine Hansen, rightly told me that the packaging tape acts very much like the orb, or the magnetic orb in Takahashi's 2004 game Katamari Damacy, where small objects like spoons and paper clips adhere, and as more objects stick to the orb, it grows with jungle gyms and cars, snowballing to the point that it collects stadiums and entire city blocks. Well, my strands of tape collect soils, but also flowers, fecal matter, plastics, artifacts from human and non-human occupation, and allow me to do an ethnography of the soil. Using the wrong thing for the right purpose defines so much of my work with soils, water, and urban form. And like a mud skipper, these devices allow a user to move back and forth between field work and lab work, like the diorama captures here. Now, after scanning many kilometers of tape, I didn't have any instruments to analyze the soils. So I turned to that trusted Photoshop tool, the magic wand, which might be used like this when one wants to digitally place a tattoo on someone's chest. But I misused the magic wand to break down particle sizes. Again, using the wrong thing for the right purpose allows me to make my own remote sensing device when no data is available and no fancy instruments. And I use these techniques to not only map out, say, Allahabad and its relationship to Ganga, but also larger transects across this dynamic basin, as you see here. So these being the first kind of large-scale mappings of the basin now in about 70 years, using these very low-tech technologies. And I like to think of the drawings in terms of fashion. If most cartographic drawings are like couture, like say Christian Dior, where the measurements are customized, my drawings are more like ready to wear from H&M and Uniqlo, as they have a seam allowance so that if you gain a few kilos or lose a few kilos, they still fit. So I'm able to go even more in depth with the transect, like you can see here, to not only look at how surface water bodies expand and contract, but how this is very much tied to what is known, as I mentioned before, that hyporheic zone, where surface water and aquifers intersect. And groundwater extraction technologies like tubewells and hand pumps for human settlement and agriculture, like you can see here, all the way to cropping patterns. And it's it's this amount of silt that's been accumulated here over these many millions of years that has made this a laboratory for testing out groundwater. And in the context of India in particular, the Ganga Basin has the greatest potential for groundwater extraction, which is why it's been such a major site for testing out groundwater technologies in the 20th century. And throughout this process of doing this work, I'd constantly stumble upon advertisements like you see here from Crompton Greaves, where the tubewell is always drawn in section, and the farmer is extolling the virtues of the tubewell in terms of more water and more crops. And this resonated with what I began to draw, where you see here the patterns of urbanization going from left to right. You can see the relationship between, say, river and riparian, nalas, ponds, canals, tubewells. There's a kind of thinning out of urban density because the tubewell allows for a kind of decentralization to take shape. So it's much more supportive of spreads and densities that allow people to domesticate landscapes. That's also why so much of the Indo-Gangetic plains and other parts of the world are more defined as a kind of spreads and densities than, say, kind of major urban areas. And while I have an abridged time wall in the exhibition, trust me, I'm not going to go over that in this talk, but I do think there are a few moments that are helpful to situate then how the tubewell taps into this incredibly large commons of aquifers in the world. It's first patented in 1865 by an American by the name of Byron Mudge, who patents this technology because he's a troop in the American Civil War and is worried about Confederate troops poisoning surface water. So he patents this technology to be used to draw up groundwater so that they would not run the risk of being poisoned by Confederate troops. And he said as much, that this was a war technology, but also a technology that was very useful for a camp or a household as well. By the 1867, The Tubewell starts to go global. It's taken up in London and is also used by the British in the Abyssinian expedition, where British troops are moving across the Abyssinian desert in present-day Ethiopia, and they rely on this technology to draw up groundwater. And it's from there that this technology really starts to go global. We start to find any number of examples of the Abyssinian Tubewell, of bullock pump, for the colonizers or colonies. So it's very much also tied to histories of colonialism and imperialism, not just within the subcontinent, but other parts of the world as well. And celebrated very much for the clean water that it draws up. It was written about in the Lancet and many other medical and science journals at the time for the advancements that it brought in terms of stopping, as they put it, all atmospheric influences. But the Tubewell really starts to become very important in, of all places, Arizona in the United States. In 1898, a case is filed where there's a dispute over groundwater. And just to give you a little bit of a kind of pocket history of water rights in the United States, which is very common across much of the common law world, which of course Pakistan's part of, India, Kenya, much of the Caribbean, is that there's what's called first in time, first in right. So I have water, I'm drawing water. Anybody can come and draw water as well, but they cannot take out so much water that I can't take out the same amount of water that I'm taking every year. So that's what first in time, first in right means. Well, someone claimed that groundwater was effectively a subterranean river and that someone was taking out groundwater at a rate greater than it could be replenished, so that there was first in time, first in right should apply. Well, the Arizona Supreme Court and then the United States Supreme Court said that in fact this was not the case. That groundwater is not the same as surface water because, as you can see hopefully in this video, the Supreme Court said that it oozes and percolates from the ground. So it is a contingent part of private property and not of public property. And this came to define not only groundwater rights in so much of North America, but other parts of the world as well, where property rights and groundwater rights are incredibly implicated with one another, which has allowed for this kind of atomistic approach that prevails across so much of the world today. Now, tubewells in the subcontinent, particularly in the Ganga Basin, were originally powered by the Ganges Canal system through turbines that were placed along it through the falls, this being one of the longest canal systems in the world, constructed by the East India Company, further extended by the Raj, and then after partition as well by Government of India. And here, this is a kind of relic of one of those turbine sites for producing electricity. Turbines are no longer there. It's now more a popular place for donkeys and lovers to scrawl their names, like you can see here. But the tubewell is also incredibly important in terms of the green revolution. You know, we can see here on the other side, in Punjab in India, a kind of Punjabi farmer with his high-yield variety wheat thrown over his right shoulder. We see a tubewell in the corner, DDT being sprayed, and a tractor in the background. It's an incredibly important implement to the green revolution. It wasn't so anticipated, though, that this would be an incredibly important technology for cities. And so hopefully this image now looks a little not only familiar to you, but again speaks to the ways in which it's still oftentimes spoken about, at least in India, as a kind of agrarian technology that oftentimes is today powered by diesel energy. Strangely enough, in the context of the state of Arizona, because groundwater was dropping so precipitously, Arizona, for those of you who don't know, is one of the reddest states in the United States, meaning incredibly Republican, like home of Barry Goldwater. It's the only state in the United States that adopted a civil code for managing groundwater, enacting police powers to try to do that, and still not being able to try to control the amount of groundwater that's being extracted versus replenishment. Part of the problem with that is that most of the groundwater in Arizona is about 14,000 years old. So it's incredibly old. It's fossil water, effectively. But this map shows how incredibly contested this underground commons is and how critical it is, say, to Arizona. But if I were to, instead of looking at this in, say, a kind of policy wonk, or oftentimes people in law do, and instead think of it almost more like an architect meets geologist, where I'm looking at a kind of core sample or profile like you see here, Imagine I do that where I take a core of the earth, so you can see our little houses up there, the tube wells poking through, and then all the strata. But instead of thinking of it in terms of compression like this, I do a 180 so that I hang the core sample from the ceiling so that it's in tension as opposed to compression. And I do this so that we reorient how we see the subsurface as a protagonist in the shaping of life on the surface. And so a mirror below allows us to then see the surface reflected below. And so here you can see, this is Loni, which is just outside of New Delhi, where this is the reflection, and then we can see on the other side all of the tube wells that are poking through. So sometimes you have to look down to look up, and look up to look down. And I do this at 4 different scales. I look at the scale of the house, both in the Sonoran Desert and the Indo-Gangetic Plains, the scale of the neighborhood, the city, and the larger region. The house that I'll show you in New Delhi was constructed as part of a model village program that was launched in 1954, designed by Jacqueline Turwitt, that you see her here next to Prime Minister Nehru. And it was supposed to be a model village that showcases new homes that could be constructed across India post-partition that would be low cost. And of the 100 homes, which included homes built by the Asbestos Company of India, Aluminium Company of India. No one thought about groundwater or sanitation other than just one house that was strangely designed by someone who used to work for Monsanto by the name of Harold Hay. He designed growing house that you see here with the hand pump in the center. And then it's a multi-generational house that grows like a pinwheel around the pump. So there are 4 kitchens surrounding the pump, and then the courtyard there, and then toilets and animal husbandry are held at its edges, so that you can see here hand pump in the center, kitchens at its edges, and then the spaces to try to keep the bathrooms and mangers as far away from the groundwater as possible. At the same time that this was being built, a house was being built in Arizona that similarly had a tube well, not a hand pump, but a tube well, and its own septic system as well, but had to go much deeper in order to hit groundwater that you can see here. And I'm showing you this because even though we might not think Sonoran Desert, Indo-Gangetic Plains, they have very similar spatial patterns because of the ways in which private capital is oftentimes used to access these commons known as aquifers. And here you can see both of these houses hanging upside down, Sonoran Desert on the left, New Delhi on the right. And I also then explore that the scale of the neighborhood and how the hand pump and tube well is undergirded cities and neighborhoods. In this case, one outside New Delhi, Loni on the right, and then Winter Haven, which was a community designed in Arizona that relies on community tube wells. Loni has originally was set up with a master plan in 1961-62. And it's a city that was meant to survive on groundwater, or a temporary neighborhood that was supposed to rely on tube wells, but today it relies on about 12,000 privately owned hand pumps in order to access water. And I then look also at this at the scale of, say, a city, here looking at Pikachu Basin and New Delhi, and the ways in which groundwater extraction, imagine, we have 2 tube wells here. Well, we take out so much water that the soils start to get closer together. So we have what's called subsidence, cities sink. So you can see here the ways in which these crevasses open up, like in Arizona, that are sometimes 1 kilometer long. Or we have sinkholes that emerge as well in these areas, like this here. So effectively, accessing and taking out groundwater is sometimes having an effect like a tornado or a cyclone does, in that it doesn't respect private and public property. So it raises all kinds of questions about who is responsible for the cleanup after these kinds of conditions of subsidence occur. And then lastly, I do that at the scale of the hinterland as well. looking at the ways in which, say, places like Arizona, you can see the crop circles and the greenfield urbanization taking shape, have very similar patterns to the kind of agrarian conditions one finds in Noida and Gurgaon and so many other parts of the Indo-Gangetic plains that all rely, again, on the tubewell as much as on the elevator to reach those kinds of heights. And so I take a kind of X-ray perspective here of the aquifers beneath New Delhi. And you can see the Delhi Ridge is this kind of dark, ominous cloud. So all of those golden rods there are we estimate that there are 1 million privately owned tube wells in the greater Delhi metro area. So that's almost one tube well for every 30 people. And here you can see a little bit better, hopefully, that kind of X-ray of all of those tube wells being sunk. The reason that they're shallower on the right side than the left is because the soils are mostly Himalayan on the right, and it's a much older soil regime that we have on the left. So one acts more like a sponge and one's a little bit drier, and so we have to go much deeper within it. But I'm showing you this in relationship to the major ring roads and the metro, because those we understand as being very large public infrastructures. But when we see it here, it's a much larger commons of groundwater, yet there's no way in which this has been very much visualized, let alone understood in terms of its part-to-whole relationships. And then up above, you can see also all of the surface water bodies within the area. So I do this not just for New Delhi, but I also look at it in the context of Phoenix, Tucson. I do it in Addis Ababa in Ethiopia, which survives on groundwater. Jakarta, where here you can see the Bay of Java. There's a lot of saltwater intrusion. Jakarta is sinking faster than Venice because of the numbers of tube wells that are being used to extract mostly water for drinking. Certainly Mexico City as well. So it's a kind of global phenomenon. And here in the exhibition I had at Yale, I place these portraits of these 5 cities with some of the several hundred of the many thousands of patents that have allowed for these cities, of course, to thrive, but also threaten to bleed so much of the earth dry. And I think we can see, hopefully, in these portraits, the ways in which if tube wells continue to be aggregated privately and not understood as being a collective or public resource and space, that this has quite dire consequences for not just cities, but also agriculture as well. And a lot of the work that I do then is both in the form of exhibitions, op-eds, books, workshops, because I think, one could be incredibly brilliant at what they do, but if you don't have a very careful way and expansive way of sharing your work, you're going to lead a very lonely revolution. So for this reason, I try to work across many mediums and methods. Otherwise, we're likely to suffer the consequences of sight without the benefits of insight. Thank you.